In graphical perspective, a vanishing point is a point in the picture plane that is the intersection of the projections of a set of parallel lines in space onto the picture plane. When the set of parallels is perpendicular to the picture plane, the construction is known as one-point perspective, and the vanishing point corresponds to the oculus or eye point from which the image should be viewed for correct perspective geometry. Traditional linear drawings use objects with 1 to 3 sets of parallels, defining 1 to 3 vanishing points. Vector notation. The vanishing point may also be referred to as the direction point, as lines having the same directional vector, say D, will have the same vanishing point or converge at the same vanishing points. Mathematically, let QC be a point lying on the image plane, where f is the focal length, and let VQC be the unit vector associated with Q, where h equals 1/2. If we consider a straight line in space S with the unit vector NSC and its vanishing point versus, the unit vector associated with versus is equal to NS. Assuming both are assumed to point towards the image plane. At the vanishing point, lines parallel to the other two axes will not form vanishing points as they are parallel to the image plane. This is one-point perspective. Similarly, when the image plane intersects two world coordinate axes, lines parallel to those planes will meet at infinity and form two vanishing points. This is called two-point perspective. In three-point perspective, the image plane intersects the x, y, and z axes, and therefore lines parallel to these axes intersect, resulting in three different vanishing points. See also Property 1 below. Theorem. The vanishing point theorem is the principal theorem in the science of perspective. It says that the image in a picture plane pi of a line L in space, not parallel to the picture, is determined by its intersection with pi and its vanishing point. Some authors have used the phrase, "the image of a line includes its vanishing point." Guidebald de Del Monte gave several verifications, and Humphrey Ditton called the result the main and great proposition. Brooke Taylor wrote the first book in English on perspective in 1714, which introduced the term vanishing point, and was the first to fully explain the geometry of multi-point perspective, and historian Kirsty Anderson compiled these observations. She notes, in terms of projective geometry, the vanishing point is the image of the point at infinity associated with L, as the sight line from O through the vanishing point is parallel to L. Vanishing line. As a vanishing point originates in a line, so a vanishing line originates in a plane alpha that is not parallel to the picture pi. Given the I point O, and beta the plane parallel to alpha and lying on O, then the vanishing line of alpha is beta pi. For example, when alpha is the ground plane and beta is the horizon plane, then the vanishing line of alpha is the horizon line beta pi. Only one particular vanishing line occurs, often referred to as the horizon. To put it simply, the vanishing line is obtained by the intersection of the image plane with a plane parallel to the ground plane, passing through the camera center. For different sets of parallel line, their respective vanishing points will lie on this line. The horizon line is a theoretical line that represents the eye level of the observer. If the object is below the horizon line, its vanishing lines angle up to the horizon line. If the object is above, they slope down. All vanishing lines end at the horizon line. Properties of vanishing points. 1. Projections of two sets of parallel lines lying in some plane pi a appear to converge, i.e., the vanishing point associated with that pair, on a horizon line, or vanishing line H formed by the intersection of the image plane with the plane parallel to pi a and passing through the pinhole. Proof. Consider the ground plane pi as y equals c, which is, for the sake of simplicity, orthogonal to the image plane. Also, consider a line L that lies in the plane pi, which is defined by the equation ax plus bz equals d using perspective pinhole projections. A point on L projected on the image plane will have coordinates defined as X equals fx, Z equals f, Arizona Y equals fy, Z equals fc, Z. This is the parametric representation of the image L, of the line L with Z as the parameter. When Z infinity, it stops at the point equals on the x-axis of image plane. This is the vanishing point corresponding to all the parallel lines with slope are in the plane pi. All vanishing points associated with different lines with different slopes belonging to plane pi will lie on the x-axis, which in this case is the horizon line. 2. Let A, B, and C be three mutually orthogonal straight lines in space, and Virginia Xi, VB Xi, VC Xi be the three corresponding vanishing points respectively. If we know the coordinates of one of these points, say Virginia, and the direction of a straight line on the image plane, which passes through a second point, say VB, we can compute the coordinates of both VB and VC3. Let A, B, and C be three mutually orthogonal straight lines in space, and Virginia Xi, VB Xi, VC Xi be the three corresponding vanishing points respectively. The orthocenter of the triangle with vertexes in the three vanishing points is the intersection of the optical axis and the image plane. Curvilinear and reverse perspective. A curvilinear perspective is a drawing with either 4 or 5 vanishing points. In 5-point perspective, the vanishing points are mapped into a circle with 4 vanishing points at the cardinal headings N, W, S, E and 1 at the circle origin. A reverse perspective is a drawing with vanishing points that are placed outside the painting with the illusion that they are in front of the painting. 1-point perspective projection. Pietro Perugino's usage of perspective in the delivery of the Keys fresco at the Sistine Chapel helped bring the Renaissance to Rome. An example of perspective using 2 vanishing points. Detection of vanishing points. Several methods for vanishing point detection make use of the line segments detected in images. Other techniques involve considering the intensity gradients of the image pixels directly. There are significantly large numbers of vanishing points present in an image. Therefore, the aim is to detect the vanishing points that correspond to the principal directions of a scene. This is generally achieved in 2 steps. The first step, called the accumulation step, as the name suggests, clusters the line segments with the assumption that a cluster will share a common vanishing point. The next step finds the principal clusters present in the scene, and therefore it is called the search step. In the accumulation step, the image is mapped onto a bounded space called the accumulator space. The accumulator space is partitioned into units called cells. Barnard assumed this space to be a Gaussian sphere centered on the optical center of the camera as an accumulator space. A line segment on the image corresponds to a great circle on this sphere, and the vanishing point in the image is mapped to a point. The Gaussian sphere has accumulator cells that increase when a great circle passes through them, i.e., in the image a line segment intersects the vanishing point. Several modifications have been made since, but one of the most efficient techniques was using the Hough transform, mapping the parameters of the line segment to the bounded space. Cascaded Hough transforms have been applied for multiple vanishing points. The process of mapping from the image to the bounded spaces causes the loss of the actual distances between line segments and points. In the search step, the accumulator cell with the maximum number of line segments passing through it is found. This is followed by removal of those line segments, and the search step is repeated until this count goes below a certain threshold. As more computing power is now available, points corresponding to 2 or 3 mutually orthogonal directions can be found. Applications of vanishing points. Camera calibration. The vanishing points of an image contain important information for camera calibration. Various calibration techniques have been introduced using the properties of vanishing points to find intrinsic and extrinsic calibration parameters. 3D reconstruction. A man-made environment has 2 main characteristics: several lines in the scene are parallel, and a number of edges present are orthogonal. Vanishing points aid in comprehending the environment. Using sets of parallel lines in the plane, the orientation of the plane can be calculated using vanishing points. Tor and Coelho performed extensive investigation in the use of vanishing points to implement a full system, with the assumption that the environment consists of objects with only parallel or perpendicular sides, also called Lego land. Using vanishing points constructed in a single image of the scene, they recovered the 3D geometry of the scene. Similar ideas are also used in the field of robotics, mainly in navigation and autonomous vehicles, and in areas concerned with object detection.